Just a moment.
You can share, Elisabetta.
The recording is
on.
Okay, thank you.
Yeah.
Okay, can I start?
Yeah, you can start.
Okay, thank you very much. So hello everyone. Thank you very much again. Thanks to the organizer for this invitation. It's a great pleasure for me to be here today and participating into this webinar series about coherent multidimensional spectroscopy. What I would like to discuss with you today is about the use of these techniques for the characterization of nanomaterials. And to be more precise, I'm going to show you how we apply 2D electronic spectroscopy to semiconductor quantum dot materials towards quantum technology applications. I think that today with this particular audience, I don't need to explain too much and to spend too much time, right, describing the 2D electronic spectroscopy technique and explaining the advantages of having a multidimensional response like represented here with respect to having a more conventional 1D spectrum. I just remember that the outcome of a 2D ES measurement is a 3D matrix of data, like represented here, where we basically can follow in time, along this T2 dimension, the time evolution of a frequency-frequency correlation map. Now, the peculiar physical origin of the signal appearing in this multidimensional response is such that the response is sensitive to couplings and transport processes, which are mapped at a position off diagonal in these correlation maps. And the technique is also sensitive to coherent dynamics, that is the time evolution of coherent superposition of state that we are actually originating with, that we are creating with a specific pulse sequence that we are using to perform the spectroscopy. This coherent dynamics is manifested as oscillation in the signal amplitude, that is also called quantum bits, right? Oscillation in the signal amplitude at specific coordinates along this T2. Now, the sensitivity of 2D ES technique to couplings, to energy transport processes, and to coherent dynamics made the technique particularly suited to study relaxation dynamics and energy transfer processes in complex multichromophoric systems. In particular, the technique was initially historically applied to biological antenna systems, and a previous speaker in this webinar series already show you result obtained applying 2D spectroscopy to this interesting light harvesting complexes. Then later, the technique was also applied and exploited to characterize biomimetic artificial multichromophoric systems. Here, I'm just showing a few examples coming from my lab. And more recently, the technique started to be employed also to characterize nanomaterials, like, for example, plasmonic nanoparticles and nanomaterials, transition metal dechalcogenide layer structures, and semiconductor quantum dot material in solutions and in solid state. And I would like today to focus my attention exactly on this last family of nanomaterials, that is quantum dots in condensed phase, basically. Now, I was mentioning in my title that we want to use 2D electronic spectroscopy on quantum dot materials toward quantum technology application. Now, quantum technologies is a family of technology that are a very exciting research field right nowadays. And quantum technology wants to fully exploit the quantum mechanical nature of matter. In order to devise materials and devices with improved performances. The most familiar and the most known example is of quantum technology is quantum computing, for example. Now, in order for quantum technology to become real, we need to prepare materials where quantum mechanics and quantum coherences can be initiated, can be controlled, and can be exploited, preferentially at room temperature and in ambient condition. Toward this aim, we need a big effort in material science because we need to design and prepare materials capable to sustain coherence. And quantum dot materials appear to be particularly promising for these purposes. On the other side, we also need an effort in characterization techniques because we need to characterize, study, and investigate such quantum coherence and assess which materials are better than others. And this is where 2D electronic spectroscopy can really make a difference and can really play a crucial role towards quantum technology applications. Just to show you this approach and just to spoil what is going to be the final message of my talk today, this is how we mean to apply and to use 2D spectroscopy for quantum technology application. So basically, we started from material science engineering, and basically we design and prepare quantum dot-based solid-state materials that we cast in a solid-state form and that we included and prepare in the form of a real devices. This picture here represents the third generation of the device we are using for our quantum technology applications. Now, the coherent behavior of these samples, of these devices, have been assessed by means of 2D electronic spectroscopy. And actually 2D spectroscopy also allow to screen and to select the best materials with the best coherent behaviors. Then 2D electronic spectroscopy response has been simulated by means of quantum mechanical methodologies, by means of suitable excitonic Hamiltonians, and the simulation of the 2D response was used to perform quantum information processing. Basically, this quantum mechanical simulation allow us to read a multidimensional 2D response as a multidimensional tensor of logic variables used for massively parallel and highly efficient quantum information processing schemes. And quantum information processes is one of the examples, right, of quantum technologies. I'm going to show you now a bit better the details behind this, this final project, this final aim. Let me start from the materials, from the quantum dots. We decide to choose quantum dots as the material for this project because quantum dots are materials with very interesting optical and electronical properties. They are versatile systems. You can basically tune the photophysical properties of them, modulating the size, the ligand, and the solvent. This is the typical figure, the typical image we use, like to explain that if you change the dimension of the quantum dot, you can have absorption from the red side to the blue side of the visible spectrum. These samples are typically stable. They are easy processable, so it is very easy to prepare solid-state films out of them. And they are characterized by a dense manifold of states, and this is very important. This is an important prerequisite in order to exploit their response for quantum information processing. We decided to start from a very prototypical quantum dot material, which is cadmium selenide, because there was already available a wide wealth of literature about the photophysical and dynamic, or the main photophysical and dynamical properties of this material. So we wanted to start from something easy for our investigation. We started this journey where we applied 2D electronic spectroscopy to quantum dot material, characterizing by 2D electronic spectroscopy a very prototypical example of quantum dot, this cadmium selenide, zinc sulfide, core shell quantum dot, studied as a suspension in chloroform. We applied two different experimental scheme, in particular a fully non-collinear boxcar geometry and a partially collinear pan probe geometry. For those of you that are not familiar with the technicalities of 2D spectroscopy, this just represents two different exciting geometries, which allow us to explore different time windows, different power condition, different experimental condition, right? To check in the wider possible picture the properties of these systems. So we applied this to configuration to these samples, and we could really characterize the electronic structure of this sample and characterize also the rate constants dominating the relaxation dynamic within the system. Here I am showing you the result of a multi-exponential global fitting. What you are seeing here is the amplitude distribution of each one of these rate constant written here. This is the experimental result of the global fitting analysis. And this is a sort of modeling which allow us to really attribute a physical meaning, right? A physical process to each one of these time constant regulating the relaxation dynamic of this quantum dot. This was interesting because we could characterize the hot excitons and multi-excitons relaxation dynamics, but we could not find any signature of coherent dynamics here because any possible quantum beating due to the coherent dynamics evolution within the quantum dot samples was actually covered by the solvent contribution. This is a common problem when you study quantum dot suspension, because typically quantum dot are prepared in suspension of organic solvents like toluene or chloroform, and this solvent has a high nonlinear response, no resonant in this case, right? And therefore, I mean, the beating behavior of this signal was completely dominated by the vibrational modes of the molecule of the organic solvent, and these vibrational modes were basically covering any other quantum beating phenomenon due to quantum dot. So it was immediately clear that we need to get rid of the solvent in order to characterize the quantum coherent behavior of the samples. And this is why we ask our material science collaborator to provide us with the quantum dot in water, because water has a very low non-resonant response, and water does not have any vibrational mode in the, let's say, window that we are interested in for the quantum dots. Having a sample of quantum dots in water requires an exchange of the typical ligand that are used to stabilize the quantum dot suspension. And in particular, we got sample having with the dot having a 3.3 nanometer diameter, and with a ligand which is this mercatopropionic acid, able to keep the quantum dot stable in water. Here I am showing you an example of a 2D frequency-frequency correlation map recorded at a particular value of the population time. Once we got rid, we removed, right, the contribution of the organic solvent, we could really capture and measure the coherent behavior of the dots. And indeed, the time evolution of the signal was showing several beating during time. The signal was dominated, for example, here in the maximum of the signal. The most important beatings are low frequency beating, these ones. The frequency here is about 200 wave numbers, and this corresponds to a well-known and a well-characterized longitudinal optical phonon. Looking at off-diagonal position, so where this phonon was contributing a bit less, we also find higher frequency beating. Here I'm showing you a zoom at early times. These beatings are characterized by a frequency more or less of 1200 wave numbers. Now we analyze the behavior of these beatings, first of all, looking at where they were contributing the most. Here I am showing you the amplitude distribution of this peculiar beating frequency in the rephasing and in the no-rephasing signal. As you can see, we have a contribution of this 1200 beating mode, mainly at the off-diagonal position in the rephasing signal and on diagonal position in the no-rephasing signal. For those of you that are familiar with the assessment of quantum beating in 2D spectroscopy, this is the typical situation you expect from a electronic coherence. We also analyze the time behavior of these beatings, and this is the result of the application of a bilinear transform. This is a smoothed pseudo-Wigner-Will transform. The result that we obtain applying this bilinear transform to this trace here is a 2D plot like this one, where you have on the y-axis the frequency of the beating. And as you can see, we have this predominance of this 1200 beating that we already found calculating the Fourier transform, right? And along the x-axis, you have the time. And this is showing you basically the dephasing time of each one of the frequency appearing on the x-axis. And as you see, we have here the 1200 beating is basically over in 200 femtosecond, and this corresponds to a dephasing time of about 35 femtosecond, in agreement with what one expects for more or less an electronic coherence. The simulation of this sample and these optical responses actually allowed also to identify with better precision the electronic state that are giving rise to this coherent evolution, this coherent dynamics in the 2D spectra. And indeed, we could verify that this coherent dynamics can be ascribed to a coherent superposition of fine structure states belonging to different exciton manifolds. So we are basically attributing this quantum beating to an interband electronic coherence. Basically, it is the coherences I am pinpointing here with the red and the yellow arrows. Starting from this evidence and from having found that basically 2D spectroscopy can really capture quantum coherent behavior in suitable conditions, so for example in water when the solvent is not contributing and so on, we decided to study more complex systems. So we decided to complicate a bit more the materials, and rather than studying isolated quantum dots in solution, in suspension, we prepare dimers of quantum dot by means of this dithiol ligand. And we studied dimer of quantum dots both as suspensions, so in solution, and both as solid state sample. Here I am showing you that we actually tried several deposition techniques in order to obtain solid state sample with slightly different optical properties and morphological properties. Why to move to this dimeric system? Because the possibility of having interacting quantum dots allow to build the delocalized wave function in specific conditions, and this represent an additional handle to engineer coherence in the system. So if you have more complexity in your system, you have a more complex electronic structure, and therefore you also have the possibility of build with your laser pulse sequence a higher number of coherences that then you can follow in time with 2DES. And this was specifically the aim of realizing these more complex samples. Of course, we wanted to move to solid state because when you envision the preparation of a device, you always think to something that is in the solid state rather than in form of a solution. The design of the materials and also the experimental measurements have been guided and driven by simulation. And this is a sort of image summarizing the kind of simulation our collaborator did for us. Here, I mean, in this panel D, you can actually see what I mean when I say that the dimer has a more complex excited state structure. These are two single dot. When you couple, right, and you turn on a coupling among them, then you form a dimer. And the dimer, if the coupling is high enough, as new eigenvector and new eigenfunction, this delocalize new states that complexively represent a more complex structure than the single monomer actually has. Now, simulations also suggested important guidelines for the design of the material. First of all, in order to have the formation of an effective dimer, you need to have short distance between the two dots, and this is kind of intuitive, right? This is why we use this very short ligand. The ligand in the experimental sample is half nanometer, more or less. Second, they found that we need to have small dot. So the typical dot that the people study, the 6 nanometer diameter dot, are not suitable to obtain the localized coherences. You need the dots with the diameter smaller than 3 nanometer, more or less. Actually, this is also this revealed to be challenging sample, because the small quantum dot with diameter of about 3 nanometer absorb on the very blue wing of the absorption of the visible spectrum, and this is a very unlucky region for 2D spectroscopy. This is really difficult because there is very difficult to achieve a compressed ultra short pulse. So this is also, like, say, a challenging spectral region to perform 2D spectroscopy. Moreover, we also studied and assessed the role of size distribution. Size distribution is something that you can never avoid when you prepare a quantum dot sample. You will always have a distribution of sizes in your final sample, even if, I mean, material science techniques can reduce the size dispersion. We found that 5% size dispersion is an optimal value. 10% is still acceptable. A size distribution wider, broader than 10% may give some problem in the ensuing, let's say, detection of coherence, because of the phenomenon known as fake decoherence, where different coherences with different frequency actually overlap and then get washed out. Starting from this, we got the materials, and here I am showing you an example of experimental and theoretical data obtained on 2 different dots, one with a diameter of 2.8 and the other one with a diameter of 3.5. So we are always talking about a small quantum dot. On the upper line, there is the simulation. On the lower line, there is the experimental data. The matching between experiment and simulation is acceptable. Even more importantly, what is acceptable is not is the match of the time behavior. So, for example, I am showing in this on the right here the experimental time behavior of the signal at this position here, at this cross-peak coordinate. Blue is the experimental beating, and red is the computed beating in a very, let's say, in a very short time window. And as you can see, for both samples, for both sizes, there is a pretty good match between experiment and simulation in terms of frequency of the beating, phase of the beating, and time behavior, defacing time of these beatings. This good comparison, this good parallelism between experiment and simulation also allowed to identify the state involved in these coherences. And we could assess also through the comparison among different samples that what we are seeing here is the evolution of a superposition of state delocalized over 2 dots. So what we are looking here is an inter-dot coherence, basically. And this is clear if we compare the simulation upper line and the experiment lower line. for the dimeric sample, SQD and BQD. S is a small quantum dot, 2.8, and B is big quantum dot, 3.5 nanometer. And this is instead the monomer sample. And the plot I'm showing here has this famous bilinear transform, showing you the, in this case, it is the X and Y axes are inverted. And so basically you see the frequency of the oscillation here and their time behavior. And we could really see that when we have dimer, there are coherent features that are not present when there are only monomers. So we can really ascribe the coherent behavior to inter-dot phenomena. Interestingly, the time behavior of this coherent dynamics was longer than what we expected, because the defacing time here, both according to simulation and both, I mean, in terms of experimental data, the defacing times here are a bit longer than the intradot coherences, and this is about 100 femtoseconds. Here I am showing again the beating trace at cross peak position, and this is again our bilinear transform, showing that our 1000 wave number beating here is lasting a bit longer than what happened in the sample with only monomers, so for the intra-dot coherence. Now, why are these inter-dot coherences living a bit longer than the intra-dot ones? This is still a matter of investigation. We are still trying to understand the origin of this phenomenon, although theoretical simulation are suggesting that this behavior can derive from the peculiar properties that has this delocalized wave function, delocalized over at least 2 quantum dot, like drawn in this scheme, in this cartoon. Okay, just to conclude, I would like to bring your attention on this paper, where our theoretical partners actually used and exploited the 2D ES response we measure on the dimeric sample. And they interpreted this 2D ES response as a tensor of logic variables, and they use this tensor of logic variables to perform a quantum emulation. They actually emulate the dynamical behavior of a 3-atomic molecule. So this is a first proof of concept of how it is possible to really use 2D electronic spectroscopy response as a hardware to calculate, to emulate quantum systems. It turned out that the emulation and the quantum information processes that they could actually achieve, right, with this peculiar scheme is, let's say, is as efficient as a quantum computation. So the scaling goes with the square of the number of states addressed. This is for the peculiar sensitivity of 2D electronic spectroscopy response to population and coherences. And all this, I highlight, was done at room temperature, because all the 2D data I've shown you were taken at room temperature. So this really represented the first example, very simple, right, a proof of concept indeed, of how it is possible to really exploit 2D ES response as hardware for quantum information processing, which is one of the possible quantum technologies application. Okay, with this, I would like to conclude with a few final remarks. 2D ES can really be used to study coherent dynamics in quantum dot samples under specific conditions, right? And the simulation and our experimental works highlighted that you need a specific condition in order to be able to measure such coherences. We have guidelines now to engineer materials with somewhat wanted coherent behavior. In dimeric sample, we could obtain a much interesting situation with a much more complex electronic structure and a much more interesting also coherent behavior. And we have a first proof of concept in which we successfully applied this 2D ES response as hardware for quantum information purposes. Future development, very quickly, go to greener material. I said at the beginning that we were using cadmium selenide because this was the easiest material to start with. Cadmium selenide is not a green material though, so we want to move to lead sulfide or other materials without cadmium or selenium, right? Move to more complex structure. I mean, dimers were really successful. Should we try trimers or even more complex structures? And then also going to address doubly excited state in order to exploit not only single excited state, but also higher energy manifold of state. And this would complicate even more the electronic structure we can address with 2D spectroscopy. And so it will provide even more logic variables to perform quantum information processing. With this, I conclude. I thank who is paying for my research, and of course my research group, because these guys are really the one that actually make measurement in the lab. And you, of course, for the attention. And I am finished.
Thank you very much. So the floor is open for questions. So I have a question regarding the dimers, where you see the longer coherence time. Couldn't that be a result of exchange narrowing? Yeah. So when you delocalize over two molecules, you will, if it's perfectly delocalized, you would get a square root of 2 longer decoherence time, right? So
exactly,
the explanation.
Yeah, this is exactly the kind of explanation we are looking at, right? This is what I meant when I said a behavior due to the specific nature of the localized. This is analogous, right? Okay. Coming from the field of molecular aggregates, right? This is exactly the same kind of picture and vision. Yes, yes.
And there's a Q&A question.
Should I look to the chat?
No, I think I will read it. I'm not sure. Cheng Yun Wang has a question. I'm not sure if you want to ask it live. Oh, he's already promoted. Yeah, you can ask the question.
Yeah. It's very nice presentation, Professor. So my question is that what is the time for electronic coherence defacing in CDSE quadrat? Thank you.
Okay. Yeah. So the dephasing times we found for, let's say, the conventional intra-dot coherence. So for monomer of dot was more or less 30-35 femtoseconds, in agreement with the previous measurement that also other groups actually provided on different or similar quantum dots. The dephasing times becomes a bit longer when we have dimers, and this was exactly what Thomas was mentioning before, right? And probably because this the localized nature of the eigenfunction give rise to a sort of motional narrowing effect, which keeps the coherence time a bit longer. This is at least our hypothesis so far.
Okay, thank you.
You're welcome.
Thank you so much. Yeah.
Okay, there's a question from Pavel.
Yeah, you said that for the dimers, it's favorable to have smaller dots, and that's why you have to go towards the blue edge of the spectrum. Can you maybe elaborate why is it better to have smaller dots? Thanks.
Yes, this is more, I mean, a question for my theory collaborators, but basically when you have smaller dot, it looks like the wave function has a longer leakage outside the dot. So when you have smaller dot, you can have actually higher coupling. This is also, I mean, you can even think this, I mean, in my experimental mind, if you have a very big, since the distance between the dot is counted among the center of the two dots, the bigger is the dot, right? If you count twice the radius, the distance became longer. So this is why if you try to do dimers with like 6 nanometer dots, this is not going to give rise to a quantum behavior like the one we need. So this is the point. And actually, yeah. Please.
Yeah, and this coupling, then this goes beyond something like dipole-dipole, right? Interaction.
Yeah, this goes beyond. And this, I mean, in this simulation, they have dipole-dipole, they have exchange interaction, they have all sort of couplings, right? When you put these two entities close together. Yes.
Indeed. Okay. Yeah, cool. Thanks.
I would like maybe to continue this question, if I may. What if you simply begin to deposit these quantum dots without any ligands in between them? Okay, so simply, sticking them together, because you can also do that, for instance, high concentrations in something like polymeric matrices. Of course, then you will have all possible variations between them, but then you can enhance the coupling even more.
Yes, this was exactly an attempt we did, and yes, this is what my collaborators call the naked quantum dot, right? The point is that this was the very beginning of an investigation, and we really wanted to have known entities. So we wanted to be sure that we have a dimer, so that our theory partner could really take a dimer, right, and simulate the dimers. So we wanted to build a sort of theory experiment parallelism. Of course, to be very practical, right, to move to a strong coupling, a big complexity, this naked deposition, this deposition of naked quantum dot would surely be something to try. And we actually have such a sample. We actually measured them. They reveal to be also complex from an experimental point of view, because they give a lot of scattering. It was very difficult to get a decent signal. So this is why we decided to stay with the, let's say, more ordered, probably less efficient, right? But just that we can have a clear picture of what was going on there, experimentally and theoretically.
And then again, well, another question is about, so these are supposed to be spherical quantum dots, right?
Yes.
How spherical are they? Because if they are kind of elliptical, right, you begin to have the splitting between the first excited states.
Yes. So basically, we consider them as spherical. I think we had from TEM measurement a sort of experimental confirmation that the deviation are not too big, right? Are not too significant. But you are right. In the size dispersion, there is also dots that are more elliptical than spherical. We decided not to include this in the simulation and in the interpretation, but this is something that we need to take care of in the future, because of course, I mean, the non-spherical ideal shape give rise to splitting that indeed may change a bit the electronic structure.
Okay, thank you. Darian, can you ask your question live?
No, we can't. Now. He does not have a microphone.
Oh,
are there changes? So Darian Morrow asks, are there changes in relaxation time, not defacing, in the quantum dots in water versus organic solvent cases?
Not really. I should say, however, that we are investigating, I mean, here I'm showing you, for example, we are investigating a very short time window. We are investigating basically half picosecond. So in half picosecond, at least in this measurement here. So in this time window, we do not expect to see relevant relaxation dynamics, right? But we didn't find a significant variation among different quantum dots, all, let's say, with the dimension not far from 3 nanometer in diameter. And in water, actually, we also tried the different ligands, shorter, longer ligands in water. We tried topo, we tried the different kind of thiols ligands. So in this spectral window, there is no significant differences in terms of population relaxation, let's say.
Okay, then the next question is coming from Jon Schultz. Please go ahead if you can.
Hi, good morning. Thank you so much. Marvelous work. That was spectacular. I just wanted to ask, and I think you've already answered some of this to a certain extent, how many dimer aggregates do you think are present in these ensemble measurements? And have you explored additional channels for minimizing these system-bath interactions in these sample configurations?
So if you are asking me the number of dimers we have in the sample, I can only answer many because
Sure.
many, because I mean, when we do experiment, we do not really count the dimers. We look at the optical density, because in order to have a signal, right, you need to have a colored sample. So the typical rule is having absorbance optical density of 0.1 or less, right?
Sure.
So I would say there is a huge number here of dimers and of dots. Also, 2D electronic spectroscopy is an average technique. The response is an average response because it is a phase matching. We have a precise phase matching relationship. So I cannot envision this particular experimental configuration with monolayers or single dots or single dimers. I don't know if this was the question. Not with this technique, right? You need to envision single molecule to this spectroscopy. I know that there is people working on that around the world, but it is still a challenge to work on single entities having this level of complexity of the response.
Thank you. Thank you very much.
Can I ask a quick question? Is there any fluorescence from these quantum dots?
Yes, in the solution, the fluorescence got quenched in solid state. So you are thinking about the fluorescence detected techniques.
Exactly. Yeah. So
Yeah,
one could do that, but then you would have to do it in solution. But then you want anyway. You would like to have, if you want to do it single molecule, right? You don't want to have a concentrated sample. So maybe it's possible then.
Yeah.
I think Lawson-Lloyd is the next. Lawson-Lloyd, you can ask your question. We can't hear you, Lawson-Lloyd.
We can shift to another question. Okay, so
yeah, maybe we should go to the next one.
Yes, at least for the moment. Okay, so yes, Sankaran, you can ask your question now, I understand. Sankaran Ramesh?
Yes, thank you.
Okay, good. This works.
Yes, my question is about the fake decoherence that you mentioned. How do you identify or distinguish if you have fake decoherence to emphasize this portion, let's say?
Good question. Not experimentally, because experimentally you will just measure the phasing time. Now, the fact that we can say that the fake decoherence is a less significant effect is because we know the size distribution of our sample, which is in the order of 5%, and through the comparison with the simulations that are actually simulating the 5% distribution. So there is the simulated response take into account this. But experimentally, you are right. I mean, you cannot really tell. I mean, maybe we have a much longer dephasing time in a single dot, right? But we don't know, because what we measure is an average effect. So experimentally, it is very difficult. Just looking at the 2D response, I mean. Then you can have some hint. I mean, knowing the size distribution from the people who actually made the quantum dot for you. This is the point.
So this the defacing time for this kind of fake decoherence also falls in the same time range as the electronic coherence.
Sorry, I couldn't hear you very well,
sorry.
actually.
The defacing times are also of the same range as electronic coherences. Is it?
Yes, they are electronic coherences. Yes.
I see. Okay. Thank you very much.
Okay, the last
Okay.
question from, I think, Lawson. Lloyd, if we can hear you. No, we can. We
No.
cannot.
Okay. So
Then maybe we are stopped with that, Thomas, and we
yeah,
move to the next
exactly.
one.
So if there's no final question, then let's thank Elisabetta again, and then